Hello, this is David Scher, back for another installment in Physics 572, Introduction to Health Physics. Unit we're on is dealing with interactions of charged particles with matter. I hope we can finish that up and then move on to the biological effects of radiation. So let me share my screen and we can begin. Today we're going to talk about alpha and beta particles. We've talked about electrons, we've talked about alpha particles, but there are a few nuances that I want to cover this time. Then we'll give some examples at the end from medicine that might help explain show the practical use of some of this material. So we said before that charged particles, when they pass through matter, their electric charge there's a force on the electric charges in the matter, the electrons primarily, at least initially, and they interact with each one of them and give up energy as the charged particle passes through matter. It gives up energy to each electron that is nearby. It slowly and continuously gives up its energy, imparting energy to all those electrons. They excite or ionize the atoms that the electrons are part of. At the rate of energy deposition, DEDX, is inversely proportional to speed. So as the particle slows down, it gives up more and more of its energy. That's why the ionization increases as it goes deeper. At the end of its path, it's traveling very slowly and can interact with the atomic nucleus and deposit a lot of energy through those interactions. And so the range is the dE divided by dEdx over the entire energy, over the range of energies that it has. It starts off with E0 and ends up at 0. That gives us the range of the charged particle in matter. Last time and showed you that data for the stopping power, the dEdx, and the mass stopping power, where that's divided by the mass density, is available on databases from NIST, the National Institute for Standards and Technology. It's a great resource, and we have a lot of information available to us. In the past, we weren't so lucky. We had to rely on formulas, empirical formulas that were approximate, very close and good enough for the kind of calculations we need to do. So these are some of the formulas that have been used. If you don't have access to the details on the internet, these formulas are quite valuable. And so in different regimes, energy regimes, different formulas are applicable. This formula here is based on expressing the energy in MeV and the range in centimeters. And it gives us the range in air. Sometimes we'll be interested in the range in some other medium. We call it, it's used in this slide, the symbol is R sub m. And if we express that in milligrams per square centimeter, we can take the range in air in milligrams per square centimeter by dividing the distance by the mass density, and relate to other media by this formula, 0.56 times the atomic mass number to the third power, the cube root of the atomic mass number. So that's just an empirical relationship between the range in different media and the range in air. We know the range in air from the formula we have. That's one relationship. Another that's well known is the Bragg-Kleeman scaling formula. And here it is on this slide. If we know the range in some medium R2, and we want to find the range in some other medium R1, are related through the densities, the mass densities, and the effective mass numbers. So if we know the range in medium, and that's the way things have worked, if we know the range in medium, then we can use the density of range of air. we can use the density of air. It's 1.23 10 to the minus 3 grams per cubic centimeter. And the effective atomic mass of air, 14.6 grams per mole. It's because air is composed primarily of nitrogen and oxygen. Add up their relative contributions, and this is the number we get. Well, then, if we substitute in the numbers for air, we call R2 the range in air, then in the numbers for rho 2 and M2, we come up with a formula for the range in any other medium. It's 3.2 10 to the minus 4 times the square root of that effective atomic mass divided by its density times the range in air. That's a way to calculate from air to another medium. But this formula top is good for any two sets of media. Here's an example worked out. It's not the ranger, it's the range. I will fix that before I post these slides. So this is the range in tissue based on the range in air. So the thing that's helpful here is that the atomic number in tissue is quite similar to the atomic number of air. Air, as I said, is made of oxygen and nitrogen. Tissue is made of carbon, hydrogen, and oxygen, so they're very similar atomic numbers. And if you work it out, we know the density of air. We just went through it here. We know the density of tissue. It's close to 1. It's not exactly 1, but the ratio is 1.293 times 10 to the minus 3rd. And so because the mass numbers are the same, we don't have to, that becomes a 1. And so this is the equation that relates the range in tissue to the range in air. And so, and these are expressed, I think, in areal density, grams per cubic centimeter, and grams per. So the point is that going through tissue, the range is much shorter, a thousandth of what it would be in air. Okay, so as it notes here, a sheet of paper or the dead layer of skin is sufficient to stop most alpha particles. Let's talk about the range of beta particles. You've seen this distribution on the right before. When beta particles are emitted, the electron shares its energy with an antineutrino, and so you have a range of energies in the beta particles that are emitted. That distribution is characterized by an Emax and also by an E average. So when we're trying to find the range of radiation coming from a beta source, we're really interested in removing all the beta particles. So in that case, we would want to use Emax. So the energy that we would use to find the range of beta particles would be Emax. Then we can go to our tables or our database and find out what the range is for an electron with energy Emax. Okay? And so we had a formula that we learned for a monoenergetic electron range. So for energy, the range for a monogenetic electron given by these formulas. And so we would use Emax to determine the range that we're interested in if we're trying to shield out beta particles. And this is a graph showing those formulas over their different regimes where they're applicable and showing that they match up nicely. This is expressed in milligrams per square centimeter. This formula is in grams per square centimeter, and that explains why the front is multiplies it differently. Okay, but what about beta particles? Well, then I just said the point I wanted to make. You use max energy to determine the range. We were shielding everything out. Now let's talk about the bremsstrahlung produced by beta particles. That's one of the ways in which beta particles or electrons lose energy in material. They give electrons pass through matter, they give up their energy through bremsstrahlung. This produces photons of radiation. When the incident electrons have relatively low energy, below MeV range, hundreds of keV range up to MeV, then is lost to radiation is a small fraction compared to the amount of energy lost to collisions. I showed you the different graphs, and there were several orders of magnitude difference. The formula that relates those two for monoenergetic electrons is that the fraction of energy for electrons that goes into bremsstrahlung is about 10 to the minus 3 times Z times the energy of the electrons in MeV. Okay? It's a very close approximation to the fraction that's produced. For beta particles, the fraction of energy of the beta particle that is transmitted or changed and converted into photons is 3.5 10 to the minus 4 E, and we use beta max in this case. Now, I do want to point out that this number, 3 10 to the minus 4, is about a third of 3 times 10 to the minus 3. And we saw before that I don't have it right here, that the average energy is about a third of the endpoint energy. So the difference of fraction is largely due to the difference in the overall energy of the photon spectrum, or the electron spectrum, the beta particle spectrum. Some electrons are giving up a lot of energy, they have more energy, they have more bremsstrahlung produced. Some have less energy, less bremsstrahlung produced, but on average, the average fraction of energy that's transferred to beta particles is close to the average energy of the beta spectrum. Now, the maximum energy of the photons that are produced is going to be related to the endpoint energy that can bremsstrahlung X-rays all the way up to the endpoint energy of the beta particle can be produced. And so it's a matter of thinking through, are we interested, is this phenomenon we're interested in something that's an endpoint situation, like what's the maximum energy, or is it an averaging phenomenon, like what fraction, what portion of the energy is converted? That helps guide us as to which concept we use, whether we use the endpoint energy or the average energy. So, as I said, as you, here it is, the average energy is about a third, average energy is about a third of the beta particle energy. So I remember putting that slide in. The spectrum is continuous, and the DEDX is a function of energy as well. They're both function of energy, and when you factor the two together, it turns out that the number of beta particles that penetrate a certain depth is approximated very well by an exponential, similar to the formula was used for photons. The number of beta particles at some depth is equal to the number that was at the surface, and then attenuated by e to the minus mu x. Mu in units of square centimeter per gram, x in grams per square centimeter. The exponent has to turn out to be a pure number. So the formula for mu, determined empirically, is shown here, 18.6 Emax minus 0.036 to the minus 1.37 for tissue, and for air it's 16 Emax minus 0.036 to the minus 1.4. This is Emax, that's in MeV, and X, as I said, is in grams per square centimeter. And here's a plot showing the exponential attenuation as a fraction of beta particles that are present after it passes through a foil of different thickness. Okay, so this is a slide that shows what the spectrum looks like and the fact that the average energy is a third of the maximum energy. Now I want to talk a little bit about an application I do want to point out that if we're trying to determine the amount of energy deposited in a material, in a person, in water, in any material, then we're going to be interested in using the average energy. If we calculate how many beta particles are emitted and how much energy they carry and assume all that's deposited close by in water or tissue or whatever material, then we would use E average because we're averaging out all the beta particles. If we used E max and assumed every beta particle carried the maximum energy, we would overestimate how much energy is deposited. So I think you're going to have a homework problem related to this concept. You're going to be asked, given a certain amount of material in a body, I believe it is, how much energy is deposited per second. And so you're going to calculate how many decays per second, the average energy carried per decay, and then you have the average energy that's deposited per second. Okay. Now I'm going to talk about an application of this all to medicine. Electrons, photons, protons, and alpha particle are all used to treat cancer. Now I'm going to jump ahead to next week's lecture and mention that cells that are undifferentiated, that are rapidly dividing, like those in cancer, are more susceptible to radiation damage. We'll talk more about this next time. So, because they're more damaging to radiation damages the cancer more than it does the healthy tissue, then we can use techniques to kill the cancer cells and spare the healthy tissues nearby. And so we're going to talk about the physics we just learned about interaction of radiation with matter. Talk about how that applies in this situation, how it's used to help make these treatments work. So let's first look at electrons. Electrons are used. Now, what do we know about electrons? Electrons have a definite range, that they deposit energy pretty uniformly up to their range because they sort of scatter in all different directions. The electrons do have the Bragg peak, similar to, or have higher energy at the end of their tracks, but because their tracks bend around and go in all kinds of different directions, the energy that's deposited is pretty uniform. They don't continue to go straight and therefore give more energy at the end of their tracks, or deeper in the tissue. The energy is spread around. And so here's a graph showing the percentage of dose at depth from electrons, and you can see it's pretty uniform to the depth, within 10%. And so it gives uniform dose to whatever its maximum distance is. Now, I do want to point out that when we talk about the range of charged particles, and particularly about electrons, there is this tail that spreads out beyond what you would have thought would be the range by the continuous slowing down approximation. And that tail is caused by bremsstrahlung. So energy is, the electrons don't give up all their energy locally. Some of the energy is transmitted by bremsstrahlung, and so there's energy deposited beyond what would be the range. In any event, so because all this energy is deposited uniformly and very close to the surface, electrons are used to treat superficial lesions. Skin tumors or tumors that are close to the surface can be treated with electrons. Okay. The next type, let's talk about photons. This is probably the most common kind of therapy. Photons can penetrate to greater depth. Remember that higher energy photons are more penetrating. Lower energy photons are readily absorbed by the photoelectric effect. And so high energy photons are used to penetrate deeply into the tissue. Photons do have a higher energy, and then they reduce by an exponential, e to the minus mu x. We just talked about it for electrons. And so the way we get tumors concentrated, or radiation concentrated in the tumors when we use photons is that we use multiple beams, focus the radiation from many different directions. So they all these beams overlap where the tumor is. They all add there and have a high dose. The doses from each individual one is much lower to the surfaces around that are not in the treatment volume. So that's a technique we use for using photons and the way it interacts with matter. They're penetrated, they can go deep into the tissue, and then by using multiple beams, we can reduce dose to the nearby healthy tissues. Protons can also be used like the photons, and we can take advantage of the Bragg peak so that the protons can penetrate, give up some energy along their path, but deposit a lot of energy at the end of their path where the tumor could be located. Because the depth of penetration is a function of energy, we can tune the energy of our protons so that it goes to the depth we're interested in treating. And so that's one of the techniques. Another technique we can use is, suppose the tumor has an extent. It's not a point. It's over a extended distance. One thing we can do is have multiple proton beams, or beams with different energies, and then deliver them for different amounts of time. And if we add up all the energies from these low energy, medium energy, high energy protons and add them all up, it turns out the total dose can be spread out over the tumor, and the dose to this tumor can be much higher than the dose to the normal tissues nearby. If we had to use x-rays, then we would see a higher dose near the surface, and we would have to use our multi-beam techniques to reduce the dose away from the tumor. Okay, so this is a very clever technique. It requires very expensive equipment that's not readily available yet, but it is very common. It is found in many places. It's used for some particular types of tumors where nearby structure is very radiation sensitive, and so we need to make sure to reduce the dose nearby, and we can do that better with photons than we can with photons. Another thing now, we talked about some kinds of external beam. What about radioactive material? Well, with radioactive material, we can inject, well, first we can bind our radioactive atom to some molecule that has an affinity for the tumor. And so if we have some chemical, some molecule that will attach to the tumor and not to healthy tissue, and we attach our radioactive isotope to it, then the agent will carry, that chemical will carry our radioactive material to the tumor, and all of the energy will be deposited locally at the tumor, not to other healthy tissues. It's a very precise way to target the tissues. Now, if we use gamma-emitting radioactive material, then we can form an image, and we'll talk about this, I think, later in the semester. We can use that technique to use those gamma rays to develop an image of where that tumor is located, where that target is located, and help with diagnosis. If we attach an alpha-emitting nuclide to it, well, alpha particles have a very small range, deposit a lot of energy in a short distance, and so we can deposit a lot of energy to the tumor, but not to the other tissues that are further away from the tumor. So that's a technique that's used for this purpose. Okay, well, that's what I have for today. Tonight, I believe homework is going to be due, and so I'm looking forward to seeing those. And I will give you your next homework that will cover this material on charged particle interactions. Thank you for your attention. I'm looking forward to hearing from you. Look forward to seeing your homework tonight, and then moving on with the semester as we go.